The talk will be given by Charguéraud from INRIA, and he will talk about OptiTrust, producing trustworthy high-performance code with source-to-source transformations.
Hello. So in the past 25 years, there's been a lot of progress in terms of increasing expressiveness. So our community now has made fantastic progress, and we're able to verify most programs that are out there. So what's next? I speculate, yes?
What did you just say?
If you take maybe I should say an algorithm or data structure, or some, even if it's concurrent and so on.
Most kinds of programs.
Most kinds of programs, not most programs. I speculate that the next era will be about increasing productivity. Focus of how can we make formal verification a more productive task. So why do I think, why productivity? I think one obstacle to adoption of program verification is related to performance. If you have a verified implementation and you want to go to a company and say, oh, you can replace your code with mine, they're going to ask, is your code at least as fast as ours? You know? But the problem is code running in production has been optimized, and these optimizations have made the code size grow and the complexity of the size of the code grow. So it has made the task of verifying this code a lot harder. So the question I would like to ask today is, how can we produce formally verified high-performance code at a reasonable cost? So to describe more precisely the challenges specific to high-performance code and present my approach, I'd like to take you for a few minutes to dive into the world of high-performance code. So I'm going to take an example from the OpenCV library, which is a computer vision library, and look at the box blur program. So you want to produce a new image where each pixel is the average of the nearby pixels from the original image. And the way it's implemented is by processing the rows and then the columns on each direction, computing sums using a sliding window. And then at the end, you can sum up the result of the two phases, and later you can do a division step. So we're going to look at the code that that computes the sum over the rows. So the specification is very simple. It just fits in this one formula here. For every pixel, for every color component, we're going to do the sum of a few nearby pixels to the right. And if you want to write the naive implementation, that is the executable specification that corresponds to it, you're going to get 3 nested loops like this. So now, how far do you think the optimized code is from there? Yes?
Question about the edge.
Yeah. Oh, we make the image smaller, should have said, sorry. Yeah. So let's look how far is the actual implementation. So I'm going to click on this link. So we get to the OpenCV page. It says it's the world's biggest computer library. There's a link to GitHub, and then you can get to this, among hundreds of algorithms, to this row sum function. So it starts here. So the code spans over a bit more than 100 lines. We have the source and the output arrays, and then we can see that the code is specialized. So it's specialized if the blur area is of size 3. Then you can do just the sum of 3 values, or if the blur area is of size 5. I hope you can read here. And then in the other cases, it's specialized over whether the image is a grayscale image. So CN color channel number is 1. Then there's just a simple sliding window. If it's an RGB image, more code. If it's RGBA image, more code. And then we get to the final default case that has the computation with the loops in just the right order. Okay. So that's more than 100 lines of code. And then if you look at the code for the columns, it's more challenging because for rows, the values are nearby in memory, but for columns, vectorization is harder to get. So the code just goes over and over like this. It gets worse and worse. And then you get to the end of the line. It doesn't. Okay, so this is the kind of code we are looking at. And the problem with this kind of code, not only it's costly to write, it's very hard to get right, and I believe it's beyond reasonable to verify directly this kind of code. But also it's a nightmare to maintain. If you want to change the algorithm or change the target hardware, then you have to go over all this code again. So that has motivated alternative routes using tools to generate this kind of high-performance code. Tools such as Allied, TVM, or Pataya. So I'm going to show you an example from TVM, the most canonical example, which is matrix multiply. It's actually quite representative. So matrix multiply, if you've read it naively, we have the 3 loops. And today we are going to look at the optimization of matrix multiply for matrices of size 1024 by 1024. This is the output provided by TVM for their optimization script. It performs 140-50x on 4 cores, so it's worth applying this kind of transformations. I'm not going to read all the details with you. I just want to highlight a few of the features that make this code work faster. So this code introduces the transpose matrix for B, because that improves the memory access patterns. There is a blocking mechanism, because that also improves locality and enables parallelization. And then the results are not accumulated directly in the target RSC. They're first accumulated into arrays of size 32, which can be mapped to registers. Then those registers are copied into intermediate blocks, which are also transposed. And then only at the end, the results are accumulated in the final array. And moreover, there was a loop in the middle that was manually unrolled because otherwise compilers are not able to spot how to vectorize it. Okay, so these are the kind of things that go into this process. So with TVM approach, you would like to start with a naive code that is a specification of matrix multiply, like this here. But actually, you need to be explicit about the introduction of the transpose of B. So the code you provide is looking like this. So you define the transpose of B, and then you can define C in terms of the transpose of B with some blocking mechanism here. And once you've said that this is the kind of high-level algorithm you want to optimize, you can write what they call the schedule, which is a bunch of hints on how to optimize the code. All right, enough low-level code. Let's just take a step back. So I've just shown you 2 possible ways of producing high-performance code. One is you just write the code by hand. That's generally applicable, but it's costly and error-prone. Or you can use one of these specialized compilers. You just rewrite the algorithm a little bit, and then you provide a bunch of hints. And you can get to an implementation that is fast, but not necessarily the fastest, because there are some optimization that fall outside of the tools. So 2 approaches, but neither of them is satisfying. Right? So now let's come back to the main question. My initial question was, how can we obtain formal guarantees for high-performance code? The question that just come across from this tour in high-performance code is, how do we engineer the production of such code in the first place? And my claim is that solving these 2 problems at the same time is actually going to be easier than solving them independently. Okay? And then I'm going to explain what's the plan. So the idea is that we are going to start from a code that is verified, maybe using some interactive tool, and we are going to have at hand the invariance of the code. And from there, we're going to apply transformation steps. So the user is going to say, at this point in the code, I want to apply that transformation. And with sufficiently many transformation steps, we're going to get to the fastest implementation. Moreover, each transformation is going to carry through the program invariance so that they will be available for justifying the transformation, the fact that the transformations preserve the semantics of the code. And if things go well at the end, we can even get a proof certificate asserting that the optimized code satisfies this specification without the tool being part of the trusted code base. So this is a long-term plan, and what I'm going to present today is the current state of OptiTrust, which is doing slightly less. We're going to start from a reference implementation annotated with shape invariance, loop invariance, and ghost operations. And we're going to apply transformations that will carry this information through all the steps. And at the end, we'll get an optimized implementation, which will know as the same semantics as a reference implementation. Yes, Robert?
So you say that you are going to preserve the invariance throughout this, but I guess the invariance is also going to change. I mean, if you're talking about loop invariance, because you are going to, so you're going to transform the invariance and keep track of.
Yes, we are going to, I'll explain later, but we are going to change and adapt the loop constructs and we are going to add ghost operations to make sure that the code continues to type check as we make transformations. So I'm going to illustrate this on a restricted language, which is a small subset of C, a restricted logic, which is a small subset of separation logic, describing only the shapes of the data, not the values inside. And so far, we've only implemented transformations that appear in the case studies. There are hundreds more that you might want to implement. So I'll present OptiTrust on the 2 case studies that I've mentioned. We have a third one about particle simulation, which I'm not going to have time to show. And then I'll dive with you a little bit into the implementation of OptiTrust, explain how we convert between a C-like syntax and an imperative lambda calculus, explain how we compute usage information during type checking, and this usage information, how we exploit it to set up correctness criteria for the transformations. Okay, so let me start with a matrix multiply example. This is a copy of the naive code we had before with additional annotations. So these reads like separation logic permissions. So you have read-only permissions on A and B. We also describe the size of the data. And we're going to have full permission on C so we can write results into it. The arrays have been flattened out here. This is a typical thing done in high-performance code. So we use this macro called mindex to say I'm addressing a particular cell within a matrix represented as a flat array. Here we have a few ghost operations that we'd like to remove in the near future. These are to say, okay, I own the full matrix, therefore I own a specific cell in that matrix, so I can do a read into that cell. So this is the input code for the OptiTrust transformation. And here, this is what our optimization script looks like. So it's implemented as an OCaml script. Each line consists of the name of a transformation, a few arguments, and in brackets is a target. It's describing a specific point in the code. And we have a special language for describing targets in a concise way. So it's time for a demo. So when I run the script, it can produce a trace like this with the steps on the left. And for each step, we can see the diff, so either on the code or on the code and its contracts. So let's look at a specific step. For example, so tiling, there was a call to tiling, which triggered itself a call to the tile function. So tiling a function, it was a loop on 1024 iterations. We want to introduce a blocking behavior, so we do 32 blocks of size 32 each. Okay? So this is a diff at the level of the code. And now if I ask to display the contracts, we can see that the contract for this loop has been refined to say which exact cells the inner loop is going to need. And there is a ghost operation on the outside which says that if we had an iterated star, now we need to have an iterated star of iterated stars so that the things type check. Okay? I'm not going to get into more details. I just want to highlight the fact that we can visualize information about annotations. We can also see the contexts that are computed at every point in the program. So that's mostly used when we want to debug. We also have usage information and details about all the instantiation that are done for every function. So this is usually only for developers. Most of the time, it's fine to look at the diff on the code or the code and the annotation. On the left, there's a script. As I said, there are some high-level transformations we can request, and that trigger a bunch of like low-level transformations. So if I write one line in my script, it might trigger numerous transformations. Only the leaves of this tree correspond to the basic transformations, and these are the ones inside the trusted code base. Everything that's been on top of it is outside the trusted code base. Yes?
Did you target more than one architecture?
Here we have been just looking at trying to reproduce an existing case study from TVM for a specific architecture. We have reproduced an existing case study that was from TVM, and we are just targeting a specific version of Intel processor. So the code is optimized for one specific processor. If we wanted to optimize for different processors, we might have some switches in the script so that we can have some common transformations and then transformations that are specific for different backends That's answering your question?
Yeah, it's a hard problem to all the different targets, so I didn't know how you were doing it.
Yeah,
So that's okay.
we haven't experimented with that yet, but the idea is that you could have switches in the script. Okay, any more question on the demo? Yes.
So trace here means this is, I think I get the impression just from the word trace that it's sort of it's something you check after everything is done, or let me ask the question directly. Presumably some transforms can only be applied under some circumstances.
Mm-hmm.
There are some preconditions that must be met before. So could you plausibly imagine, what do you call it, OptiTrust, to actually help the developer figure out what transformations they might even apply at a given point?
Yeah, that's a research direction that my colleague is starting to investigate. One thing I didn't mention is how you develop this script. So we have an interface that's inside VS Code, and I have a demo with one line here. If I press F6 on one of these lines, hopefully it's going to work. No, it doesn't work. Okay. Must have changed something. There's a typo here. Okay. Up. So it displays interactively the diff for that line. Okay, so it feels when we're developing the script a little bit like in Coq, you write a line, you see the result, you write the next line, you see the result. Okay. It's not as fast always as I'd like it to be, but for the moment it's still, we can develop this kind of script interactively. Okay, I'll get back to my slides. So we've been able to reproduce the same output as TVM. There is more room for improvement if we want to match, for example, MKL, a library from Intel. Then there will be more work to do. Just to show you very quickly on the other example, row sum, here we have to annotate the code, again with permissions on the matrices, but also with some pure facts saying some values are non-negative or greater than 1. And yeah, we describe the contracts for loops. And we can produce, using a script that looks like this, we're able to produce the same code as what I showed you in the beginning. Almost the same. We don't use pointer shifting, but it's essentially equivalent. Okay. All right, so let's dive a little bit into OptiTrust. So we take C, C++ syntax, mostly a subset of C. We parse it with Clang, so we have maximal compatibility. We use the Clang ML package to get that into OCaml. And then we have a translation phase. We eliminate all the mutable variables and all the left values to get into a lambda calculus. And on this imperative lambda calculus, expressing transformations is much simpler and much less error prone. So this is like our intermediate language. Then we type check the code. We apply the transformation that is requested by the user, and we retype check in between every phase. This is not incremental yet, but it should be. And then we can translate at any point the code back to C syntax, because our translation is bidirectional. So we can give feedback to the programmer in the form of diffs over C syntax. Yeah, more question?
So do you have knowledge about your memory caches? So when you do 6, that you get a good layout and so on?
At the last step,
Pardon? You eliminated local variables by introducing lambdas and made the function.
Yes.
Great. And then you're going to transform it back into some von Neumann style code. But my point is, or my question is, do you consider the cache hierarchy on which you're writing and so on? Because which transformation you choose and how you do the layout makes a big difference.
Yeah, so very important. I forgot one point. When we do this translation into the lambda calculus, we keep track of what was allocated on the stack, what was allocated on the heap, and when we go back, we use those annotations to go back to C code.
You don't have like a database or a knowledge base about the target architectures?
No, we don't have this kind of feature yet. That's an interesting direction for feature work as well, yeah. To avoid the user doing everything by hand in terms of mapping, yes. That would be interesting.
I think maybe not to put words into your mouth, but I think what Arthur is describing so far is a way of describing this kind of transformation, not a way to do the optimization search where you'll be?
Well, it seemed an optimistically simple 6. I think that's hard. That's your code generation problem, you know. And I'm just sort of responding to Peter, but I mean, you're trying to match the algorithm to the available resource, and you need to know about the available resource to match with.
Yeah, when I'm talking about imperative lambda calculus, it's an extended lambda calculus with all the kind of constructs that you need to reflect the memory hierarchy. So it's a lambda calculus in the way that we have structured bindings and we don't have left values, but the translation is essentially trivial. We just take it's just a matter of syntax, essentially, this translation. All the transformation on the memory layout and mapping and so on, that will be done already at the level of the internal lambda calculus.
So just to be clear, on your lambda calculus, you do have things like arrays and pointer arithmetic.
Yes, yes.
So that information basically about layout is preserved.
Yes, we preserve all the information. It's this idea of using a lambda calculus is mostly for simplifying substitutions and things like this, and having a clearer semantics. Okay, for the separation logic, we really use only like standard components. So far, it's a subset of separation logic, but everything has been planned so that we can get to full functional correctness invariance in the future. Yeah, so I'll skip over the details, but there's a draft paper where you can read the type checking algorithm. We go line by line, and we compute the resources available at every program point. So gamma is our set of resources. We have the pure bindings, variables, which type they have, whether they're ghost or program variables. And then we have resources. Each resource has an identifier, and that's a linear resource. In addition, we're going to compute the usage. So why do we need usage? Is because sometimes you might have a full permission, but only perform read operations. And so you actually need less than the resource you have. And this usage information, it's very important to keep track of this because the correctness criteria for transformations depend on the usage information, on what you actually needed and not on what was available. The contracts, so we annotate every function with a pre and post condition. This is standard. And for loops, we decompose the specification of the loop between the stuff, the variables that are quantified for fractions, for example, the variables that are read, the parts of the sequential invariance, so the resources that are threaded through each iterations, and what we call the parallel resources, the ones that are per iteration, that iterations use exclusively of one another. Okay? And so if this shared invariant is empty, then we know the loop can be parallelized. And for the usage, again, it will be at a very high level, but we keep track of whether a pure fact was required or produced during the execution. If it's a linear resource, we keep track of whether it was used in full mode or if it was used as a read-only resource only. And then there are more things due to fractions. Okay, and this is the formalism in which we reason about the correctness of our transformations. So this is example of loop fission. Sorry, we had one loop and we split that into two loops. So there are some criteria, sufficient conditions for dealing, for assessing that it is correct to do so. And then we have to come up with new contracts for the two loops that are created. So we have some algorithms for computing that. And we also make sure the program type checks in the end. So if you're interested in this kind of formalism, you can read that in our draft paper. Yes.
So in the previous slide, it seems that you were doing a compiler kind of thing in the sense that you're worrying about the lifetimes of all the variables so you can be compact, I guess, right? But you made it explicit here as above. So does the user of your system introduce these explicitly, or is that sort of done by analysis?
These are computed. What's explicit is that, so most of the time when you call a function, the resources are going to be picked based on what's available, and there will be unique choice. Sometimes there might be ambiguity, so you need to explain. Also, the instantiation of ghost variables, sometimes you have to be explicit. I mean, this is the same in all systems. So we have syntax for those, but most of the time this goes under the hood and working. Okay, I'd like to conclude with a few perspectives and trying to answer Peter's questions from that he suggested we address. So about adoption, so OptiTrust's approach is to trick programmers into adopting formal verification, the specification and verification, by selling them the idea that we're going to help them to optimize their code and to help them maintain the code. And to do that, well, we are going to ask them to write a little bit of extra formal information. And the more they want to optimize, the more they will have to specify. And likewise, we can trick funding agencies into funding verification by selling the fact that we're going to improve performance for AI code. What's really important for seeing this kind of technology to go into industry is integrability. So people can take their existing code base in C, they can take a single file, a single function, and rewrite this function in an unoptimized way, optimize it using OptiTrust, and then they have a drop-in replacement for that function, independently of all the rest. So they can try this technology on a small scale and progressively replace their code base if they'd like to do that incrementally. And like I said, yeah, they can start by applying transformation that don't need invariance. Then if they want more advanced transformations, they can specify the shapes. And then if they want very much more advanced transformation, then they have to go for full functional correctness. This part about full functional correctness is ongoing work by my PhD student. So I hope that within the next year we'll have made progress on this. The other question was about what is credibly achievable and on what time scale. So I think we've seen several attempts at providing specification language, practical specification language for C-like languages. And it's great that we have different experiments and we see what works and what scale up best. But at some point, it would be also nice that we have some kind of standardized way of writing INRIA-style specifications for C-style and ML-style programs. This doesn't have to be with respect to the semantics of C or of OCaml specifically. It can be with respect to an ideal language that has a nice semantics. What matters is that we come up with trustworthy transformations back to the standard languages like C or OCaml or Java or whatever. And thanks to the OptiTrust framework, we can use transformations to make the code more idiomatic towards the target language if we are going to use this path. Also, very interesting would be to build a reusable library of data structures and algorithms. Many such data structures and algorithms have been formalized in the recent years. It would be nice to have a common repository with everything expressed with respect to this standardized specification language. And the point here is that we are going to verify those once in one language and then possibly, hopefully, derive implementation in different languages. I know there are different trade-offs and optimization depending on what kind of target language you have. But again, OptiTrust is there to help you have different optimization paths from the same naive code. And at a longer scale, time scale, I think I would dream of having a unique environment in which I can write my code, specification invariants, where I can apply program transformation, I can do my interactive proofs, and also deal with feedback of interactive provers. So different frameworks have tried to combine different things, but putting everything together is a lot of engineering work, and also if we can maybe factorize this work, that would be great. Okay, finally, I'd like to thank all the contributors to OptiTrust. Damien and Becca team have been working on the development of the framework initially. Thomas has completed the case studies that I've presented, and the others that I've not presented is now interested in research directions, in particular the synthesis of proof of transformation scripts. Sorry. And Guillaume has been working on the implementation of the type checker, and is this year going to try to extend this to full functional correctness environments. If you want to read more, there's a draft paper on our webpage or on this website. OptiTrust is an open source project. It's very open to external contributions. I'd like to say it's not ready for production use. If you want to use it, please get in touch if you want to try it out. And I'll be happy to take more questions. Thank you.
Yes, I'm wondering where you are putting the bar between transformation that should be source to source versus more classic optimization passes in the compiler, because I'm assuming some compilers are implementing similar transformation in one flavor or another, and in some cases after knowing a bit more about the architecture. So is it okay to have both, or where how to choose whether you want a source-to-source transform versus something in your favorite compiler.
Yeah, so our first priority is to demonstrate how we can implement transformations that compiler don't know how to do automatically. And we just rest on the compiler for doing like the vectorizations and other things that are more specific. But in the long term, I think we could express as OptiTrust passes every passes of a compiler. There's no reason not to do this, especially if you go in terms of like in specialized hardware, GPUs or things like this. Then maybe you can, I mean, there's no reason not to re-implement compilers in OptiTrust if you can, because then it gives you more control over what might happen at a late stage of the compilation process. So the question is whether how far you can maintain code that is still human readable when you apply compiler passes. But the heuristics, if you can find a way to provide readable output for heuristics that compilers implement. But that would take a lot of work, of course.
Have you been able to find any bugs while annotating the code? Like, what's your experience? Like, if you you're tricking the industry users into using your code, presumably their code is not always free, right?
Yeah, that's a good point. So for now, we've been reproducing like case studies and existing code well tested. So we didn't expect to find any bugs in those code. But keep in mind that the idea is not to take existing code and to annotate it and to see what happens. The idea is to take existing code and just try to reproduce similar code by starting from a naive code on which we would write the annotations. And then if during the optimization process, it's unlikely we're going to get to exactly the same code. We just want to achieve a code that is similar in terms of performance or behavior or better. So I don't think this process will help you discover bugs.
So naive code, your like deductive invariance or any sort of assumptions about them are easily made correct.
It's almost, so sometimes you even want to start from the specification. So your specification is correct by default. And sometimes you start from an imperative algorithm that naively implements your specification because you need to introduce some imperative aspects that are non-trivial for the specification and that you can't introduce via transformation. But there, presumably you know what you're doing at this stage. So there one more question first here.
Yeah, I just want to ask, like last week or so, like Nuno said that like one key part of making actually Alive being adopted in practice by developers was actually having a web interface where like it's easy for developers to like just put in some code, some transformation from LLVM and directly see the result there, and also having persistent links for that. I was wondering, like you showed something which looked like you already have like some, well, it seems like this would also apply well to your thing, but like I wonder if have you experimented like with like having like a fully web interface such that you don't need to install any tool and that you can then.
That would be great. I mean, it requires setting up a web server and having some tooling running. The problem is we're running arbitrary camel script, so you have to be a little bit careful with the sandboxing. But there's also like resource usage because we are manipulating these big ISTs, performing thousands of transformations on them. So until everything is fully incremental, the resource usage is not negligible.
Can you say something about the like more specific the resource usage? Like how long does it take to like fully optimize if you do like?
Like the Matmule transformation is a few dozen, like between a bit less than 20 seconds at the moment. But we know there are like obvious inefficiencies that we have to most importantly, making the type checker incremental so we don't go over all the code every time. Yes, it was more, yeah.
So as I understand it, a lot of the complexity is sort of encapsulated under the transformations, right? So each transformation you or your students or whoever has to sort of think about, figure out what the right invariants are to various groups. Is that accurate? And so every new transformation then, that's where things start getting, I mean, that's where you have to put in work. So if I'm Mr. TVM and I want to, oh wait, I've just had this clever idea about this new way to split up loops. I would have to go back in and, So can you tell us a bit about how much work is that per transformation?
Yeah. So it really depends on the transformation. But it's very important to distinguish two groups of transformation. What we call the basic transformations, which are the ones that are going to be performing minimal changes to the AST, and for which we are going to devise correctness criteria. Okay, so for those like loop fission, we have to think really hard. Okay, this is what makes the transformation correct, and this is what we're going to implement. And then there are all the other like high-level strategies, which are going to be compositions of these basic transformations. This is also non-trivial work, but it's of a different nature, because there you don't have to think about separation logic details. You just have to think about the way you're going to apply your heuristics. Regarding the basic, one key question is, what is like the basis for being able to express any kind of reasonable code transformations? How many transformations are in this basis? So far, we have implemented about 100 of them. I believe with 300 or 400, we can cover most of the patterns that apply to generic code transformation. It's only speculation, of course, because it's hard to tell before, but when I looked at many examples by hand, I had this feeling that it's a fair number, but it's not infinite either. And it's going to take us, yes, a little bit of time to implement all of this. But then, hopefully, at some point, I can give a more precise answer to your question.
So, how many algorithms do you expect to, subject to this process?
So, is your question like what kind of codes will not be will become produced?
Codes, I'll say, and how many do you anticipate this helping?
I'm not sure like how to quantitatively answer the question. I don't really have numbers.
Well, let's say
I anticipate that sometimes
1,000 such routines, and you validate 400 transformations. I mean, and those compose, right, somehow.
Mm-hmm.
So maybe you should just optimize each one, and have one translation for each one that's as good as it can be. I guess this goes back to my thing about your target. You're going to find as you go to a richer fabric below that you're lowering those, and the transformations that you'll have there will become more complex.
Yeah, and there's also for like going to more different forms of hardware. We can also follow the roots of the EXO tool, where you give the semantics of an instruction in terms of its code, equivalent code. And so if we want to generate hardware instructions for like more exotic hardware, all we have to do is to use OptiTrust to get to the code into a form that can trigger this rewriting into the right instruction. So yeah, there are many interesting research directions for targeting different kind of hardware. And at the moment, we've been focusing mostly on the high-level transformations at the algorithmic level.
So I guess that, is it true that you basically, any sequence of transformations, if you have a proof, then this is a valid, this is a valid sort of like result state. So you have a kind of way of, someone gives you a kind of possible state, and you can say whether or not that's correct or not. One thing that occurs is that this seems like a really good candidate for reinforcement learning or kind of some AI-based heuristic optimization method. Have you thought about that at all?
That's also something my colleague Thomas is interested in trying to do machine learning on this. Really what the key challenge here is that the search space is vast. If at any point there are 400 basic transformation plus all the high-level strategies, makes you like 1,000 of applicable transformations at every step on every lines of your code. I mean, the search space is so big that maybe learning techniques can work.
Go is very big, and AI can do that. So
yes.
It's a very sparse rewards landscape, but I feel like that's what AI, these kinds of techniques are good at.
Maybe, okay, let me answer differently then. Sometimes the programmer has information about the expected kind of load to put on the algorithm, or the expected, for example, like in the image processing example, the user knows that most images are RGB or grayscale, and not with 6 color components. Okay, how is maybe it's possible, but it seems not so obvious for a machine learning technology to know about this information from just looking at the code. Maybe it could, but I mean, if you get something clever enough, it could do anything. But
I know I'm just the guy who says, like, if you tried doing machine learning a bit on it, you know, that's kind of like I'm going to do. But it's, yeah, it seems possible.
I just want to say the machine learning people have tried it. There are papers on this. So the allied people have papers on using reinforcement.
Oh, no kidding. That's awesome.
Yeah. Our search space is going to be much larger than that of Allied. So.
And then the TVM people have further follow-up on that kind of thing.
So you've been focused on kind of numerical optimization algorithms. Have you thought about other sorts of things like data structures where you might be introducing caches or changing representations from display trees to balance trees or that sort of thing?
Yeah, this is the next case study I want to do, but I didn't think about it yet. The major case study you can find on the website is it's a particle in cell simulation. Where you have particles moving around in space. And for this one, we've reproduced a state-of-the-art implementation with all the steps without the validation, like the correctness criteria. And we took, that was the third case study, we took the most critical step, which is the scaling of the values and the change of the layout of the array. And we did a check for that one step. So I'd like to complete the case study for checking all the steps. And there you can see changes in memory layouts, as well as scaling of numerical values. These are transformations that we have not seen in the two case studies yet, but I think answering your question. One last, yeah.
Yes, thank you very much for your presentation. About the tricking funding agency and tricking programmer part, I was wondering, I know that TVM is connected to a different question. TVM, under the hood, it is a statistical model. Well, it's not neural networks, but it is gradient boost, I think, the algorithm. So have you considered hiding calls to TVM behind your tool in order to provide the navigation into the search space, which is in TVM?
I've not considered that, but
I mean,
maybe we could.
But the idea, sorry, I'm
no.
not very clear, maybe I'm confused. But the idea will be the interactive part. Well, if the programmer knows what he has to do, he says, yeah, my tiling is 32 and so on, and if not, he gets TVM or another tool like it, find the right schedule.
So one thing that is would be I think interesting to try, and I do want to try in the short term, is at a given point in your script, you say, okay, please help me, and then the system will try to apply transformation, but only at depths 1 or 2, and produce a bunch of programs that you can benchmark, and then you can see if one transformation is improving performance, and that can give you some hints on how to continue from there. So that could be, but you can't benchmark like millions of versions because that's too expensive usually.
So I'm surprised you didn't build in a cost model into the.
Yeah, the cost model does not exist. That's a problem. It's really hard to tell from just looking at like memory operations how much they're going to cost. They can, if the data is in cache or if it's not in cache, you pay between 1 and 100 or more, and that's what is making not only the search space is big, but you're lacking a cost model to navigate this search space. This is what has made automated compilation so hard.
Okay, that's the end.